29 of your test review packet. Okay, so number one, position function is given. Particle moves along the x-axis for all real number values of t, where x of t is equal to t squared e to the negative t. The part A just says find v of t and a of t, so we can just find first derivative and second derivative. To get the first derivative, we have to involve obviously power rule and e to the u, but also notice these are multiplied together, so we got to go through product rule. Okay, f prime g plus f g prime. Okay, t squared becomes 2t. G function stays. Back to f. G prime, what's e to the negative t's derivative?
E to the e and then times
Times what?
u prime over u.
Not u prime over u. Yeah, so the derivative of e to the u is just e to the u times u prime.
Oh.
Yeah, u prime over u is just for natural log. Right, remember this rule? Okay, so e to the negative t times negative. Okay, let's do some cleanup here. Okay, so there's my velocity function. Okay. Okay, sorry, we're still on part A here. We're gonna want to find acceleration. Okay, so look at our velocity function here. What do we need to do to get to acceleration?
Two product rules.
Two product rules, right? Do you see that? So 2t e to the negative t. Yeah. Anytime we have terms combined together, we gotta go through product rule. Gotta go through product rule twice. Right? 2t e to the negative t, that's a set of product rule. And t squared e to the negative t, that's another set of product rule. Okay, so we'll take care of the first piece here. Okay, we'll take care of the second piece. T squared e to the negative t. some cleanup here. Finite terms. Feels a little bit cleaner if I can take out a GCF. So it looks like they all share e to the negative t. Oh, sorry, messed up here. If I distribute the negative through negative, this is okay. But if I distribute this negative through here, there's two negatives. So that gives me positive. Excuse me. Okay, so I factor out e to the negative t, I get 2 minus 4t squared. Okay, so we'll set that off to the side. We have our velocity, we have our acceleration. Thank you. Okay. Part B, determine the interval that the particle is moving to the left. Well, before we can determine anything about moving left or right, we have to create our velocity sign line. So part B. Okay. Create our velocity sign line, set v of t equal to 0. Here's my v of t. I'm going to just go ahead and take out a GCF as well. It makes it easier for me to find what I need to find. My GCF is t, e to the negative t. So factoring out means dividing it out. So if I divide out t, e to the negative t, I'm left with 2 for the first term. Second term, if I take out e to the negative t and t, I'm left with t here. Set that equal to 0. Set everything equal to 0. So I have t equal to 0, e to the negative t equal to 0, 2 minus t equal to 0. Let's see what comes with that. All right, t equals 0, that's done. E to the negative t equal to 0. If I want to bring that t down, I can take natural log of both sides. Right, but natural log of 0 is undefined, so we don't have anything here. 2 minus t equal to 0 equals 2. Okay, so we have 3 critical points. Let's place them all onto our velocity sign line. Just 0 and 2. Choose values in each subinterval to test against our velocity function. I'll choose -1, choose 1, and choose 3. So -1 goes in. -1 times e to the positive 1. So that's negative, positive, and positive. That's only one negative. So it's moving left. Okay, plug 1 in. 1 times e to the -1. E raised to anything is always positive. Okay. And then 2 minus 1 is positive. So everything is positive here, moving to the right. Okay. Enter 3 in. 3 times e to the -3. Those are all positive. 2 minus 3, that's negative. So only one negative. Okay, so moving left, we see two intervals of moving left. Right. Once you use your test points to populate your positive and negatives, right? We don't care about these numbers anymore. You're not going to use them in your statements. Just infinities and 0 and 2. The reasoning is because that's where velocity is less than 0. Part C is the particle's velocity increasing or decreasing? How do we determine that? What do we look at? Just acceleration, right? So just acceleration, a of 3. So just insert 3 to the acceleration function. E to the negative 3, that's positive. Okay, 2 minus 4 times 3, 2 minus 12, negative 10, plus 9, that's negative. So positive times negative is negative. Don't really care about the value. The fact that it's negative is all that we need. I plug 3 into the acceleration function because it's asking if the particle's velocity equals 3. Okay, everybody okay with part C? Okay. Part D says, is the particle's speed increasing or decreasing? So how do we get to that information? Velocity and acceleration, right? We need to look at both velocity and acceleration and compare their signs. So we already have a of 3, so and then we kind of know what v of 3 is, right? We kind of tested it before already, so v of 3 is negative. Okay, everybody okay? A through D. Okay, let's look at number 2. Got the key on page 32. But here's number 2. Okay, look at how this is set up here. Y equals 3 minus 5x to the x. Do we have a derivative rule that can handle this type of a setup? For part of it is a to the u, but this overall is not a to the u because a to the u would mean that it's a constant raised to a variable. Right, that would be a to the u. Like if it was like 2 to the 3x, right, that would be a to the u. Implicit. We got to do implicit. We have to, first of all, I want to make sure that we understand that this is a variable raised to a variable, right? And we just don't have anything that can handle a variable raised to a variable, right? See how the base has a variable in it, the exponent has a variable in it. We can't handle a variable raised to a variable, so we got to get it to look like a different form. And this is where we introduce logs, right? We want logs in the problem, so that will allow this exponent to be in a more usable location. Okay, so this is called log differentiation. Take the natural log of both sides. Okay. So once you take natural log of both sides, this exponent is now free to move. I can push that down in front, but no calculus yet, right? This is just power property for natural logs, for logs in general. I can move this exponent freely back and forth, and I'm not changing the overall value. Okay, so now what pops up here? Left side, okay, we're ready for our derivative now. Now that we have some options available to us, what do we have to use on the left side here? Implicit, a little bit of implicit, right? 1 over y dy dx. And right side, we have to use product rule, right? 2 to the x times natural log of 3 minus 5x. Before we couldn't do anything, but once it comes down, at least, I mean, still product rule, but at least we have something available to us, right? We can actually handle that. Okay, so f prime g plus f g prime. Remember the rule for a to the u. Now we can apply exponential rule here, a to the u, because this by itself is an exponential function. So derivative of a to the u is natural log of a times a to the u times u prime. Okay, so we go through f prime g plus f g prime. Okay, so we start off 1 over y dy dx. Derivative of natural log of y is u prime over u, 1 over y, but we need to attach dy dx because we have to collect our dy dx because of implicit. All right, f prime, that's a to the u, a to the u. We get natural log of 2 times 2 to the x times 1. Okay, g function, no changes, bring that down. F function, no changes, bring that down. G prime, natural log of 3 minus 5x. The rule is u prime over u. So -5 over 3 minus 5x. So the calculus is done. Now we're just having to do a little bit of cleanup and get things in the right place. Any questions here? This is the most important step here, getting from here to here. Pretty okay. All right, so just some cleanup steps here. We want to solve for dy dx. So what do we need to move? 1. Yeah.
In front and when to just leave it. There's some,
Yeah, with log differentiation, because you're dealing with two variable expressions, once that comes down, you're always going to have to deal with product rule.
the 1/2, and you bring it down, you just keep it as 1/2.
Exactly, right,
Okay.
right. Yeah, if it was 3 minus 5x raised to the 1/2, then I would just go through, or
Oh, just regular.
yeah, just chain rule, or if it's natural log of 3 minus 5x to the 2 or 1/2, I'll just bring it down and you just go through u prime over u. Right? There's no need for a fancy rule like this. Yeah. Okay. So that y needs to be moved over. So multiply both sides by y. I'm also doing some cleanup along the way. I'm just trying to push these two terms together to kind of get it a little bit cleaner. Right, it's not a whole lot I can do. I'm not going to ask for common denominators. Okay, so once that y moves over, there's one final thing that we can do. Yeah, bring the original back. Yep. So because we're starting with a function, our derivative should be able to be represented just in terms of x. We don't need y, but here we have y as a temporary variable, but we should bring x back. Okay. Your answer is a mess, but you can leave your answer like this. Log differentiation just naturally just going to have a messier derivative, messier looking derivative. Okay, why don't we do one more of these to make sure that so I'm going to call this 2 part B. Can't find any space on your handout or on a separate sheet. And you may not be able to tell what's going on, but we can always rewrite the problem, right? How would you rewrite this problem?
5 minus 4x to the 7th to the 1 over x.
Let's make it even cleaner here. 5 minus 4x raised to 7 over x. Yes. I mean, what you said is not wrong. It's just if I can get these two together to be just one exponential fraction. Everybody okay with that? Is this in need of log differentiation? Yes. I got a variable base. I got a variable exponent. I gotta use natural log to get that exponent down because I just don't have a rule that can handle something of this form. Okay, natural log on both sides. I'm gonna get my exponent ready here. I'm gonna call it 7x to the negative 1 because I'm anticipating when it comes down, I do want to jump directly into my derivative rule, and I want to try to avoid quotient rule when I get to that part. So bring that x up to the top, and I can do a little bit. I mean, it's a little bit cleaner with the power rule there. Everybody okay so far? Okay, what's next? Yes, but
Oh, to bring it down.
yeah, let's just bring that down, right? This is power property. 7x to the negative 1 comes down, but yes, we are going to expect quadrant rule on the right side. Since we're going to turn this into a multiplication between two terms. Okay, a little bit of implicit on the left side. Okay, f prime g plus f g prime. Okay, u prime over u. All right, everybody okay so far? Okay, move that y over and do some cleanup on the right side.
You also take out 7 over x.
Yeah, I'm not going to ask for GCF, right?
Okay.
So just try to clean up. Yeah,
Okay.
that's fine. Don't have to worry about GCF. Don't have to worry about common denominator. Just kind of get it a little cleaned up. That's all. All right, or we go with log differentiation. Okay, back to the packet. Okay, number 3. All right, looks like a mess, right? We want to start with a derivative. So use your expansion properties, right? So here's the big idea. I have in this case log of A over BC, right? You can see three different parts, yeah. Oh, sorry. This is page 30. I was pulling to the key page there, but. Okay, so if I have something in the form of log of A over BC, I can expand that into log of A minus log of B minus log of C. Right. Anything in the numerator is part of a positive log expression. Anything in the denominator is part of a negative not log expression. So same idea here. We'll treat x as A. We'll treat e to the 2x as B. We'll treat the square root as as C. And then as we expand, we're going to have to kind of let that 3 tag along to each term as well. Bring the exponent down, but just bring your numeric exponent down. We'll leave that to e to the 2x alone. So we bring that last exponent down. 1/2 comes down in front. Because e to the 2x is its own function. We can just take care of, yeah. So with expansion property, I think it's a little bit cleaner. It's a little bit more recognizable if we just bring the exponent down. That e to the 2x is good to go. We can handle that without having to mess with it. Okay, so we're ready for our derivative rule. Each of them can be applied using the log base A rule, which is 1 over natural log of A times u prime over u. So each term. Okay, so 3 stays. Log base 7 gets converted to be 1 over natural log of 7. I just put it in the denominator here. And then u prime over u, so 1 over x. Right? 3 stays. Log base 7 gets converted, 1 over natural log of 7. E to the 2x, we can go through u prime over u. So the derivative of e to the 2x is e to the 2x times 2. That handles that u prime up top divided by the u value e to the 2x. Minus, okay, 3/2 stays. 1 over natural log of 7 is a coefficient, part of that conversion. And then u prime over u, negative 6x over 1 minus 3x squared. Okay, I'm just going to do some cleanup individually within each fraction, but not going to do any common denominators here. We're just going to try to get each space cleaned up. Okay, everybody okay so far? All right, number 4. All right, take a look at everything that we have to do here. Can you list those things out? What do you
With
see?
the differentiation,
Implicit because of all the y's in the equation, right? Got to collect dy
product rule is
dx.
gonna need to be used.
Good. Product rule because it's at 3x squared y, right? We see the multiplication of different variables.
You need to expand.
We need to, yeah, we don't want to do derivative here just yet. This is too messy. You have a natural log that can be expanded, right? So expand first. Take care of this first, and then we can look at our derivative options. This is, remember, natural log of a over b can be expanded into natural log of a minus natural log of b. We can continue working with this, right? Get this to be what? How else can we rewrite this to, yeah, y to the 1/3, right? And that 1/3 can be brought down, and so it's a lot easier handling derivative at this stage than trying to do it at this stage. But this whole time we haven't done any calculus yet. We're just setting it ready for the calculus step for our derivative. Now we're ready. Each time we come across your y's, you got to collect your dy dx's. And that 3x squared y, we got to go through product rule when we get to it. Okay, u prime over u. Right. Okay, 1/3 natural log of y becomes, we keep that 1/3. Natural log of y becomes u prime over u, so 1 over y. We just took y's derivatives, we need to attach dy dx. Okay, 5 natural log of x, 5 stays. Natural log of x becomes u prime over u, so 1 over x. All right, 3x squared y, we got to go through product rule here. Okay, f prime, 3x squared becomes 6x. We keep the g function, keep the f function, and then g prime is asking for y's derivative. Y's derivative is 1, but we are asking for y's derivative. We need to attach dy dx. And what's minus y's derivative? Yeah, minus 1 dy dx. I like to put that 1 there because when you're factoring something out, sometimes we lose the fact that there's still a 1 there. So I like to put a 1 there, especially when factoring is involved. That reminds us that we still have to have something there, even when it looks like everything is gone from that term. 5x becomes 5, 3 goes to 0. Okay. Any questions there? Yes, yeah. So product rule is kind of like the overarching. Oh, you're talking about like, right. So this whole thing is product rule. There's some power rule hidden in here, but then once we get past it, then each of these are individual terms, so each of them can be handled using power rule. You only have to do product rule if you see 2 variables attached by multiplication. Right, so the calculus is done. Now we're just collecting, moving, getting the dy dx arranged. And so I have 3 dy dx terms. There's 1 dy dx term. I have another dy dx term, a third dy dx term. Okay, so I'm going to start moving them to the left side, and everything that does not have dy dx, I'm going to separate them, move it to the right side. Factor dy dx out. Divide the parentheses over. On the AP exam, if it's a multiple choice, you want to get it down to just undo all the complex fractions, but on the test, I'll be okay with your leaving your answer up there. Okay, questions? All right, find tangent line equation for the function. So tangent line equation, we can just go through a product rule, find the derivative, insert 1 to get the slope, and then point slope form. Okay, f prime g plus f g prime. E to negative x becomes e to negative x times -1. Keep the natural log. Back to f. Then g prime, natural log of x is u prime over u, which is 1 over x. So here's my cleaned up derivative. To get to my slope, just insert the x value in. So negative natural log of 1 over e to the first power plus 1 over 1 e to the first power. Natural log of 1 is 0, so that's going to wipe out with this first term here. I'm just left with 1 over e. There's my slope. I have my order pair, my slope form. Okay, let's do a derivative of inverse at a point. Let's see if I can find one here. Okay, I like to use my table chart here to kind of keep track of my progress. Ultimately, I'm looking for the derivative of the inverse at -4. I know -4 is the x value of my inverse function. So let's put all my order pair information up above and then all my slope information down below. So if -4 is the x value of my inverse, then -4 is the y value of my original function. Okay, so understand that whatever number they give you is not the x value of your original, it's the y value of your original. But this is how you're going to start the problem. Looking for the x value, you're always going to be given the y. Set equal to 0 to make it easier. So now we got to play with some numbers here. This number should be easy to find. It'll be an integer value close to 0. So try 0, 0 doesn't work, then try 1. Doesn't work, then try -1, then 2, then -2. Okay.
If it is factorable, it is, and you get two answers, do you just pick the one?
It's not going to be factorable. This is the x cubed here.
No, it's cute.
Yeah, not going to be factorable. Okay, so go through different values. What'd you get? X equals -1, right? So let's test it out, make sure it works. Insert -1 in for x. I get 2 times -1, that's -2. -2 minus 3 is -5. -5 plus 5 is 0. Right, so that's the hard part, right? Getting to, but we see that there's that relationship there between the function and its inverse. You're always going to get flip-flop order pairs, right? If order pair 1, -4 is on the function, then there's an order pair -4, 1 on the inverse.
-1.
Sorry, -1, my bad. Okay, so now that I have this, then I can work my way down to this information. Because I have my function, I have the x value. If I can find the slope of the derivative at -1, then this number will lead me directly to the slope of the f inverse at -4. So let's find f prime of x first. Right. That's f prime of x. What you guys get? Cool. So if the slope of this graph is 12, then the slope of the other graph at this corresponding point must be 1/. That's the answer. I would say values between -3 and 3. It will fall between that range. Okay. For curve sketching, I think page 7 is really a good one to look through. So look at that one. Make sure you also memorize your what your natural log graph looks like, right? If you have your natural log graph memorized, can get all sorts of information without,
Oh,
you know, like you need a calculator. Okay, it won't ask you for domain, range, limits, it's just gonna, or just ask you for relative max, relative min, POI.
Gotcha.
Not gonna sketch it.
That's right.
So we don't have to find like any asymptotes. Origin.
There's a derivative and finding relative max, relative min. Yeah, come around, see if you guys have any questions.
I have a quick question on this,
It's really stressful.
for 30s, like, how do you go from this to that, and then you do that?
So I wouldn't bring, I wouldn't bring that 2x down, because that is a nice E to the U problem. It's still messier, so I should leave that alone.
Okay, okay, I see, thank you.
No, this one I would just go line, so not long enough.
There's no way we're all.
You can, yeah, you can use the graph,
Like, we don't have.
but you can also
Like, we're not
solve it.
gonna-
on-
Yeah.
So it's nice to know both ways.
Yeah. I said like, it would only be water. So I actually. We're gonna get like, we're gonna get like, so it's gonna be like, I love it. So good, like, so they're gonna be like.
Maybe that.
It's like, silly, that's what I'm making. And then it's like, of more expensive than we expected, and I'll just like have like, my grandparents, I'll just make it. I don't need any. I think. Okay, but it's actually. Wait, where's the relative max? Yeah, how do you do that? I think if I don't have to find a minute, that it's probably gonna be -5 here, activity, so I don't think it's gonna be the critical point. It's something that you can say, like, it is my. And I was like, oh, no, no, property. It's still lit. This is all in here. I redid these two questions, which are those. Do I know?
Alright, so I know that I swear. I like it. So
Why is this negative one of it? Why is that?
Because you're thinking of a relationship between a line and a perpendicular. It's a different relationship. It's just gonna be the reciprocal.
Okay, so is this always positive?
Well, not always positive, it's just,
Yeah.
it's only flip that. So if this is -12, then you make it -12. You're just flipping the number, but you're keeping the sign. So. Oh, yeah, that's good.
Yeah, and then I, so the negatives like all good here. Okay. So spots, and then I find the first derivative, find it, plug in negative. And then that gives me this flow, and then I do the reciprocal. I just, I'm still confused for the. I hate solving things. I don't. So I'm just gonna take some of the fake.
Related to that.
Relative min. That's what it seems to be. Now I have to plug it back in.
Okay, okay, I get it, okay. Thank you. Oh, I don't like, I get that, actually, I was like that. On a big number.
Sorry. This.
I don't like plugging in, that's weird. I love this. It makes me so angry, but what is it? That's.
One is for. This. And that's one back to 0. One doesn't even exist.
Everybody has to look up first. Okay. Coach Alberts, you were like trying to. We were like trying to figure out this for us. Elevators, Emerson, Farrah? Yeah, it's just kind of just in general, when you're solving things with CNN, you like sometimes it goes to zero, and sometimes it just like doesn't exist, and I don't really. And I don't know what question they were on. But there was one that we did.
So you're saying like, e to the x equals negative one, and you're trying to solve for this, for instance?
Yeah.
So take the natural on both sides, because I cross off for x, the x term. Fine, right? I get x. The problem is this side, natural log of negative one doesn't exist. Why? Because if,
The asymptote is at one, so it makes it natural log.
guys, you can pull everything that you need from this graph, right? What's natural log of negative one?
Yeah.
Oh, that's not there.
Doesn't exist, right? So this doesn't exist, right?
So the and then you take a natural log of something like that, you can use that
Yeah,
graph.
you're just looking for the Y value, right?
So here, everything that you need is on the graph. Right? Natural log of negative one. Everything you need is something like that. You could use. This one has cleaner, but it's a very good one. So I could use this one, right?
Right. So grace.
It's okay. I think what should just say.
So with natural log of x equals one, there are two ways to do it. You can make it natural log of one is equal to one.
No.
Or figure out silver.
I'm so confused. Anytime I just follow up with me, you're like. I know I get partial credit and stuff, I'm really not like it. I just don't know how to simplify it.
I have a homework, it's got an exam. Okay. I'm not sure where I stopped showing you the homework. I don't have about 5.4.
That's really getting to zero. Okay. Yeah.
So like, you show that way you don't have to pick out like a negative integral of, like, by using. I wasn't sure, like,
Yeah.
because I need to know also how to solve, once you use shell, but like, it's still asking you to use like this one.
Yeah. I use but I'm still. I'm still looking on this. I can't do this, right?
Right.
So. Wanted to. Then I could rotate it.
Yeah.
around, build.
I understand it.
Normally, I would say that I only do. Film method, is good. I always use this mustard as my go-to.
Okay.
And if I'm stuck. Or if it's really complex.
Okay. And then for some people where it's like.
Yeah.
You're.
That's really trying to understand.
Something where it's easier to show or something like that, it's not sure, like, what the situation.
Yeah, sometimes, it's still the problem.
Yeah.
Yes, you could do after this, but it's not, you're rotating like this. You think that I two things, that's why they get solid often.
Yeah.
Because as you put it together, because definitely.
So like, do like one thing and then one. Okay, gotcha.
Or.
Which, right, right. But if it's like forcing you to do like just one. Okay, all right.
Oh, you, okay, go to 18 and then. 3 times 6 is 18 and then. Yeah. I was like, there's no way I'm just.
This one here.
This is just this.
Oh, wait, sorry, not.
No, we can't. That's no longer.
Are you looking at this?
This I can do properly. This one is not going to be on.
Just.
Guys, I need all your foot banks up front and your thumbs up.
There's no store for my rugby.
Those are all separate variable. Footboard, derivative, yeah, I think.
I think it's so bad when I took my break for like a week, my mental health went like down. So I'm like stuck up again.
If you find, yeah, you could. Keep going, spend all. Still.
Yang, I don't know if this is really late. Can I just ask you one thing? See, morning practice, I did this there. And I was confused when you said this, you got this about the east.
Yeah, so, yeah, each of the utensils, so each of 2x over each of 2x. Each of the utensils, fine, because it's not, because the natural log.
Hey, today's the 5th, sorry, 15th.